Oh, whoops. Cut me out there. Greetings. It's Friday, and what we're going to do is I just all of a sudden realized I was going to do this on Monday, and I was like, I ain't coming in on Monday. so, I mean, I keep forgetting that we have Monday off. So here I am on a Friday morning putting this together for you. What we're entering now is two-dimensional motion. Okay, and what do we mean by two? We've been going in a straight line. As a matter of fact, some of you got caught. I think most of you missed that one problem when we had the acceleration, and you thought it was 2.2 um, uh, meters per second or whatever, how fast it was going. Um, and it wasn't. It was 4.4. So that was pretty interesting. After 1 second, it would have been going 2.2 meters per second, and then we figured out how fast it was or how far it gone. So when things are accelerating, they expand. You know, if during one interval of time they've gone this far, and then when we go to the new then with acceleration in the same time interval later on, the very next same time interval they've gone this far and then this far. So you're accelerating, you're going faster. So it's a curve. It's a parabolic curve. Um, that's in one-dimensional motion. So now we're going to look at two-dimensional motion, and the main thing that we talk about is projectile motion. And the second movie that you have here has a bunch of demos. Your textbook publisher produces some pretty good demo things, but they're boring. These are more these that I've shown are a little bit more lively because they're taken in a classroom. They're unfiltered, and I think they're much better to show that how projectile motion and motion in two dimensions works. If you get nothing else out of this chapter for the rest of your life, I want you to understand that if we neglect air resistance and drag, which are huge, air resistance and drag are huge. But we still neglect them because we want to keep this as simple as possible. Something very difficult as simple as possible. Um, if you neglect those, when I launch something, whether it's at an angle or straight across, the x component of its velocity stays constant. Once it leaves the muzzle of the rifle, once it leaves your hand, if you've thrown it straight, once it's launched in the air, an arrow launched in the air, whatever, the x component of the velocity never, ever, ever changes because there's nothing working against it. What changes is the y component because the acceleration acting on it is going downward at all times. Okay, so if it goes up, it's slowing down because the acceleration is going to pull it back down. Okay, that's the main thing I want you to get out of this. Let's look at some of the, so there's our little intro, and let's look at some slides here real quick. Always fun to look at slides. Everybody's favorite. Now, this might seem kind of complicated. And yesterday, I was going to do this yesterday late afternoon, like between 5:30 and 7. I was like, no, I'm going home. But now I reread it and I was like, oh, okay, this is kind of cool. All right, so here you go. Remember when I said when you turn, the steering wheel is another accelerator in your car that causes acceleration? Well, here's a classic example. All right, here's the initial. So if we set up our XY coordinate system over here, and we say, okay, here's our initial position. Now look, it's got an X and Y component, right? Here's our initial position, and then here's our final position. Look what we have here. We've got a change in R, okay? The displacement then is this R vector minus this R vector. Now, since we chose this as our coordinate axis system, we could have chosen it here. We could have chosen it here. But still, it would be the displacement. We'd have to break this down into its X and Y components like we did in our vector fun that we were doing earlier. Okay, so we kind of, well, that's one thing that we've done is we've kind of gone from, we did the vector fun. You're like, okay, well, that was cool. That was a good, nice trig review. Now we're using it. Then we kind of broke away from it when you're learning one-dimensional motion and acceleration and velocity and what all that means. And now you're getting it different. Okay, now you're getting different. Now we're coming back to the vector thing. All right, so then your average velocity then, as it went from here to here, would be that change in r, which you'd have to use break it down into components to get the change in r divided by change in t, the time. Okay, that's your average velocity. Because we are using the change in displacement over change in time, so that gives us the average velocity. And when we took this vector, we would find the velocity, the average velocity it took to get from there to there would be it would have a magnitude and direction. The direction would be, probably going up this way. All right. Then the instantaneous velocity at this moment right here. Instantaneous velocity indicates how fast the car moves in the direction of motion at each instant of time. Okay? And when that velocity changes, and so here is the limit when we let delta t go to zero, this little calculus thing, here we have that tangent line at this point. Here's where the car is actually going. Here's the path it's actually taking. And notice we got Vx and Vy. We got an x component of x, of the velocity, and we've got a y component of the velocity. All right. Okay, let that sink in. And then when we find at a different time, we take the v naught over v, we take final velocity over the initial velocity, again vectors, find their difference. Notice how this is the difference of the two vectors at its new position. Then we get the average acceleration. Okay, notice this isn't an instantaneous velocity over an instantaneous time. It's the average acceleration, and we're always going to have our acceleration be constant. So the average acceleration is the same as the instantaneous acceleration. Okay, and then we've got our same old equations of kinematics, but now, so going in a straight line, equations of kinematics still hold. Oh, here was my average. Here's where I was showing you the average speed. Okay, so here's our four equations of kinematics. But now, when we're going up and down, Vx, V naught, Vy, so we've got to do two calculations at the same time on the same thing if it's going at an angle. If it's flying up at it, if it's flying at an angle, it's got a V. It's got the motion of it has an x and y components. All right, the motion has x and y components. Okay, so we'll get to the spacecraft here in a minute. All right, there's your intro out here for right now. This is film 1.